We're going to do some examples of integrals involving inverse trigonometric functions. Here on the screen, we have three of the most common that you will probably see. One thing to note is that each integral involves an expression squared. So part of this is we're going to be focusing on getting that expression squared. We're also going to be focusing on getting these values of 1. So those are going to be the two things as we manipulate these problems. So let's just jump into some examples. Looking at number 1, I'm probably either using arcsine or arcsecant, and I know that because of the radicals in the denominator. So what we want to do is we want to start manipulating. Now, first thing I would do is, like I said, I want an expression squared under the radical. So instead of 1 minus x, I can rewrite this to be, I still have my rad x, 1 minus rad x squared. Now we are going to be using u substitution for a lot of these. So for this one, let's let u equal to the square root of x. That means du is going to be, this is x to the 1/2. So du is 1/2 x to the negative 1/2 dx, which is 1 over 2 rad x dx. So I have my u, and then for my du, notice I already have 1 over rad x, but I want 2 rad x. So I'm going to put a 2 here. So I'm basically multiplying my expression by 1/2. That means I want to put a 2 out front, so I'm multiplying the whole thing by 1, because 1/2 times 2 is 1. So let's start replacing with u's. I still have that 2 out front. I'm going to have 1 over the square root of 1 minus u squared, and then keep in mind that the 1 over 2 rad x dx, that whole thing equals du. Notice now this looks like our arcsine integral. So I can say this equals 2 arcsine of u plus c. Last step, I want my answer to be in terms of x, not in terms of u. So I'm going to make it arcsine of the square root of x plus c. And that's our answer. Let's do another example. So for this next example, I want you to notice that I have a 4 here instead of a 1. And in all of my identities that we have the 1s highlighted in pink. So I want to make that a 1. And in order to do that, let's factor out a 4 under the radical. I'm going to be left with 1 minus x squared over 4 under that radical. From here, the square root of 4 is 2. So I'm going to say 2. Next, I still want this to be an expression squared. Right now it's an expression squared divided by 4. But what I want is something like, I have the 2, 1 minus, I'm going to make it x over 2 squared. Notice now it's an entire expression squared. From here, we want to do our u substitution. I'm going to make u equal to x over 2. du is going to be 1/2 dx. And notice that I have 1/2 dx already in my problem. So I'm going to replace with my u's. I get 1 over the square root of 1 minus u squared du. Notice that this is our arcsine identity. So this is going to be arcsine of u plus c. Last step, rewrite to be in terms of x. I get arcsine of x over 2 plus c. We have a couple more examples. Next example, notice that this one does not have a radical in it. That means we're probably using arctangent. So same thing we did before. Let's start by making this a 1. And I'm going to do that by factoring out a 2. Okay, next I want this expression to be an expression squared. Right now it's 9 times an expression squared divided by 2. So, oops, let's go back to my pen. This is going to be 3x over the square root of 2 squared. And if you need to go back, notice 3 squared is 9, then I have x squared, rad 2 squared is 2. So sometimes you have to be a little strategic about it. But at this step, we're ready to do our u substitution. Notice that most of the time, this is going to end up being your u. So u is 3x over rad 2. That makes du 3 over rad 2 dx. Now, I already have, in terms of constants, I already have a 2 in the denominator, but that doesn't really help me. So I'm going to put 3 over rad 2 in front of the dx. And let's move over my equal sign a little bit. Out front, because I want to make sure I'm multiplying by 1, I'm going to put rad 2 over 3. Let's put our u's in there. Now I'm going to do 2 times 3 in the denominator. So I'm going to have rad 2 over, this 2 times 3 is 6. I'm pulling that 2 out. I have 1 over 1 plus u squared du. Notice that this is your arctangent identity. So we're going to get rad 2 over 6 times arctangent of u plus c. Last step, plug back in for u. And our u was 3x over rad 2. Okay, we've got one more example. For this last one, same thing. Let's make this 9 a 1. Let's do that first. So I'm going to factor out a 9 under that radical. Next, the square root of 9 is 3. So I'm going to simplify that part. I'm going to have 3x in front of my radical. From here, I want to make sure that this is an expression squared. So I'm going to have 2x over 3, that whole thing squared. Let's do our u substitution. Usually the expression that's squared is going to be our u. So 2 over 3x. That makes our du 2/3 dx. Now notice that I already have a 3 in the denominator. So I'm just going to multiply by 2, and then I'm going to have a 1/2 out front. So that's going to give me my 2/3, my 2/3 dx. So if I'm thinking ahead, I'm going to be able to plug in for my u. I'm going to get my du, but we still have this x that we need to figure out. So I'm going to now isolate x with my u equals 2/3 x. That means that x equals 3/2 u. So I'm going to replace x with 3/2 u in the next step. So let's make everything in terms of u. I have this 1/2 out front. I have du in the numerator. That's my 2/3 dx. Instead of x, I have 3/2 u. And then under the radical, we have, not that anymore, u squared minus 1. Okay, so a lot going on. Next, I'm going to pull out my 3/2 because it's not part of one of my identities. Notice 3/2 is in a denominator, so that's the same thing as multiplying by a 2/3. All right, notice your 2's cancel. And then also notice that my identity that I'm going to be using is my arcsecant identity. So I'm going to get 1/3 arcsecant of u plus c. Last step, plug in. Plug your u back in. We want to make sure we're in terms of x. And that is our final answer. So those are a few problems of solving integrals involving inverse trigonometric functions.